To talk about the local mapping theorem for analytic functions, it helps to get some preliminaries out of the way. So to start with, we're going to have an analytic function f, which we'll say is just analytic at z0, so analytic in a neighborhood of z0, and it maps z0 to w0. We're going to assume f is non-constant. And then around z0, f is going to have a power series, and since it's non-constant, it's going to have a term beyond the first term that's not zero. So let's say the mth term is the first one beyond the 0th term that's non-zero. And this number m will be very important for describing how f behaves as a mapping. So it's a little different than the order of vanishing because we're not saying that f vanishes at 0. Instead, we're looking at basically how many times it attains the value w0, at least in the sense of multiplicity. So let's see. So with this setup, we have f at z0 equals f of z0, and this is what I've called w0. And then after that, the first non-zero term in its power series is just am z minus z0 to the m, and then I just have higher order stuff after that. And so as we've done with zeros, I can take f minus f of z0 and write it as z minus z0 to the m times g. So this is just factoring out the z minus z0 to the m above. And so you get a function g that's analytic at z0 and is non-zero at z0 because its value there will be this am. And this leads to the following definition. So we say f attains the value w0 at z0 with multiplicity m. And again, m is this number over here, the first m greater than or equal to 1, such that the mth derivative at z0 is non-zero. And so m, more specifically, is the order of the 0 of f minus f of z0 at z0. So here's a simple example. If I have this polynomial, 1 plus z squared plus z cubed, and here's its derivative, 1 plus 2z plus 3z squared. And so by the above, we're only going to get higher multiplicities when we have the derivative equal to 0. So whenever the derivative is non-zero, you're just going to get multiplicity 1, because this will be the first non-vanishing derivative at z0. Okay, but this is a quadratic, so it has two values where the derivative is 0. And here's what they are, just from the quadratic formula, looking where this equals 0. But the second derivative is 2 plus 6z, and so these values do not, or these values are not zeros of the second derivative, so we don't get higher multiplicity. So at these two values of z0, negative 1 plus or minus I root 2, p of z0 attains value w0. I guess I'm not saying that they attain the same value there, but in any case, the value that it attains at one of these, it'll attain it with multiplicity 2. Okay, that's just an example of how you figure out multiplicity. Let's dig a little deeper into what we've written. So far we've taken f and we've subtracted its value at z0 and factored it this way with g analytic and non-vanishing. We're going to go a little further with g and take an mth root of g. So there exists a branch of z to the 1 over m around g of z0 just because it's a non-zero number. And because of that, I can take that branch and apply it to G and get an mth root of G defined near Z0. So there exists H analytic at Z0 such that H to the M equals G. And so I should also point out that the value at Z0 will be an mth root of this non-zero number G of Z0, so it'll be non-zero too. And now we can factor f minus f of Z0 as a single thing to the mth power, Z minus Z0 times H to the M. Okay, so this is a lot of the setup that we need to prove what we'll call the local mapping theorem. So this is local mapping instead of just local description. So it's about the mapping properties. So I'll call it just a local mapping theorem. So here's the theorem. Assume f is analytic at Z0, attains the value W0 at Z0 with multiplicity m as in all the previous setup. Then there exist locally invertible analytic functions, h1 analytic at Z0, which sends Z0 to 0, h2, which is analytic at W0, which sends W0 to 0, and then such that after composing f on the left and right by h2 on one side and h1 inverse, this is basically showing that up to invertible analytic functions, f is basically z to the m. So in terms of local mapping properties, analytic functions just look like powers of z. So that's very nice. That's pretty simple. We also get out of this that there's a punctured neighborhood of Z0. So a punctured neighborhood would just mean if you put in Z0, it would be an open set containing Z0, but we've taken Z0 out. There exists a punctured neighborhood of Z0 on which f is m to 1, which means here that each thing in the image has m distinct pre-images in the punctured neighborhood. So what's happening is that f attains the value W0 with this multiplicity m. So it's like Z0 counts for m, but every other image point here gets hit by exactly m distinct values. And the reason this in particular part holds, well, we'll talk about in a second, but it's just because this holds for z to the m. Okay, so there's not too much to say for the proof. We just have to use the inverse function theorem. So maybe it's helpful to bring over all of these constructions that we've done so far. So this h1 that we need in the theorem is just going to be z minus z0 times h, because it's h's value at z0 is non-zero, so this has non-vanishing derivative at z0. And so it has to be locally invertible by the inverse function theorem. So that's h1, and that's all we need for h1. And then h2 is just going to be w minus w0. So we didn't really have to put h2 in there, but it makes it look more uniform, I suppose. Okay, so why does this work? We already said here that f has this form. So if I put h1 inverse into f, well, I'll have this f of z0 there plus then I'm putting h1 inverse into here, but this is h1, so you get z to the m. And then composing on the left with h2, that will just subtract away the w naught, so you get z to the m here. Okay, and then this in particular part, we can say precisely what the punctured neighborhood is. So let's say that h1 inverse was defined on a little disk around 0 with radius little r. And then, so this whole composition will map the disk of radius r to the disk of radius r to the m, because this is just z to the m, remember? And so under z to the m, each w that's non-zero here has m distinct preimages, and here they are. If I have w written in polar form, I would just take r to the 1 over m, and then you take all of the possible mth roots, so there'll be m of them. And you can just translate this back to the original f, because I apply h2 inverse on both sides of this here, so you'll get that that f maps h1 inverse of the disk of radius r to h2 inverse of the disk of radius r to the m. And so each w in the range of f here will have m distinct preimages, and again we have to take these punctured neighborhoods inside of the domain here, which is h1 inverse dr take away z naught. So I guess there was a typo here, but I tried to fix it in the red. So the u prime, the punctured neighborhood, will just be h1 inverse of this disk take away z naught. All right, so that proves this local mapping theorem, and there's lots of other things you can do with this, like prove the open mapping theorem for analytic functions, which we may talk about later. In the next slides, we'll get into the Lagrange inversion formula, and then we'll get into the implicit function theorem.